Hello there. In this video we're going to discuss another application of exponential functions known as radioactive decay. So if you're familiar with basic chemistry, polonium typically has 84 protons. So if we add more mass to this, so let's consider for example polonium-210, this element, or isotope rather, is unstable and emits radioactivity, right? So this is a radioactive isotope of polonium. So in this video, we're going to discuss how to model the mass and its decay over a period of time using an exponential function. All right, so through experimental processes, one can find that the half-life of polonium-210 is approximately equal to 138 days, right? So what exactly does half-life of a radioactive isotope means? So let's assume we start off with, say, 100 grams of polonium-210. So after 138 days, we're going to have half as much as we started with. So we're going to have 50G. So after another 138 days pass, we're going to have half of what we had here. So we're going to have 25 grams there. And this is going to continue the process and decay down to 0 but never approach it, right? So of course that is going to model an exponential process. So our model for those types of things is going to be equal to A of t is going to be equal to A0 times e to the kt. So as we already know, if this is our model, then A of 0 is going to be equal to A0 e to the k times 0. And that's just going to be equal to A0. So it's obvious that this number A0 corresponds to our initial amount, right? And usually t is going to be represented in time in terms of the units that we're going to be working with. So for the polonium-210, our unit would be in days. So question, what is this k, right? So this k is going to be a decay parameter, right? So this is a rate parameter. So a rate parameter. So if this is a decay problem, we should get that k must be negative. And if this is an exponential growth problem, like our principal and interest example, then this exponent k must be a positive number, right? So let's see how this sort of all works together for our particular example, right? So let us assume that we start off with say 100 grams of polonium-210. All right, so this is going to be my A0. And let's figure out what that decay parameter is. So we already know that our half-life is going to be 138 days. So usually half-life is going to be given to you for these types of problems. Okay? So if that is the case, so after one half-life, we should have 50 Gs, right? So after one half-life, so A of t is going to be equal to, so our initial mat is 100, e to the kt, and we need to figure out what our rate parameter is. So what is the rate parameter for polonium-210? So what is this? All right. So we can use this information that we have here. So the half-life is 138 days. So after 138 days, we should have half of what we started with, right? So this should be equal to half of A0, which is going to be equal to half of 100, which is going to be 50. Right? So 50 must be equal to 100 e to the k, replacing t with 138. We should have this relationship. Right? So let's write that. So that means after 138 days, we should be equal to half of what we started with, in particular 50. All right, so this is our half-life. So divide both sides by 100, we're going to get 1/2 is equal to e to the k times 138. Notice that for all these half-life problems, you're going to get 1/2 on the left-hand side. That's actually always going to be true, right? And if we were to have like a quarter life problem, then that would be a quarter instead of a half, right? So we can solve this equation for that parameter k. So we're going to take the log of both sides. So we're going to have the natural log of 1/2 is going to be equal to k times 138. So therefore, the rate parameter k for polonium-210, right, is going to be equal to 1 over 138 times the natural log of 1/2. Right, so this is the rate parameter for polonium-210. So therefore, our model for polonium-210, so capital A represents the amount after some time has passed, is going to be equal to 100, our initial amount, times e to the power 1 over 138 times the natural log of 1/2 t. So is this number negative? The answer should be yes. Remember, the natural log of 1/2 is a negative number because 1/2 is in between 0 and 1. Right? So after 1 year, how much is going to be left? Right? So remember that this unit t is going to be in days, right? So t is in days for this particular thing, right? So we need to convert 1 year into days so we can use this model, right? So this is going to be 365, right? So when t is equal to 365, what is the value of a, right? So once we do that, what do we get? So a of 365 is going to be equal to 100 times e to the power 365 divided by 138 times the natural log of 1/2. And once you work that out, you're going to get approximately 13.85 grams left. So let's look at another example. Let's consider plutonium and an isotope of it. So that's going to be 239. So plutonium-239. And let's see. So typically, plutonium usually has 94 protons. So this is definitely going to be extremely more radioactive than, say, plutonium-100 or plutonium-120 or something like that, right? So the radioactivity, or this radioactive isotope, has a half-life of 24,110 years. So it's a really long time. So let's see if we can generate our model for this. So again, the amount of plutonium-239 after some time t, and we're going to be using years for this, is going to be equal to A0 times e to the kt. So the first thing we need to figure out is what is this rate parameter, right? So remember that k must be independent of A0, right? And indeed it is. So k is always going to be equal to 1 divided by the half-life of this radioactive isotope times the natural log of 1/2, right? So therefore, k is going to be equal to 1 divided by 24,110 times the natural log of 1 over 2, right? And we actually can rewrite this in a little bit of a different way using our properties of logarithms, because it's actually the natural log of 1 minus the natural log of 2, right? So that's over 24,110. So therefore, our rate parameter for plutonium-239 is going to be equal to the negative natural log of 2 all over 24,110. Right? So therefore, our model for this is going to be equal to the amount we start with times e to the negative natural log of 2 all over 24,110 times t. Right? All right, so here's a question, because we can clearly plug in, let us assume we start off with, say, 100 milligrams. So that's going to be 1/10 of a gram. Just 100 milligrams. And how much is going to be left after a year? We can just plug in 1 and be done with it, right? So what I want to know instead, so let's ask a different question. After how long will only 1 milligram be present, right? So after 24,110 years, we're going to be down to 50 milligrams. Then after another half-life, we're going to be down to 25. Then half of that, half of that, half of that, and so on. So how long until we get to 1 milligram? Right. So we're trying to answer the question, t is equal to what when a of t is equal to 1? Right. So let's solve our equation. So we're going to have 1 is going to be equal to 100 times e to the kt. And then we can solve this generically. So we're going to have 1 divided by 100 is going to be equal to e to the kt. And we're going to solve this equation for t. So we're going to take the natural log of both sides. So the natural log of 1 over 100, which is the same as the natural log of 1 minus the natural log of 100, which is the same as the negative natural log of 100, is just going to be equal to k times t. So then we can divide both sides by k. So that means t must be equal to negative natural log of 100 divided by our rate parameter, k. Right? Okay. So let's plug in our value, k, that we obtained here. So t is going to be equal to negative natural log of 100 all over, so what was our rate parameter? K. So I believe it was like natural log of 2, yeah. So negative natural log of 2. So negative natural log of 2 all over 24, 110. So those negatives cancel, which is cool. So we're just going to be left with negative natural log of 100 all over, positive actually, all over the natural log of 2 times 24,110. So what does that come out to? So once you work out that calculation, you're going to get that t is going to be approximately equal to 160,183.37 years. So 160,000 years approximately. So it's going to take a pretty long time. But anyway, that's just another application of radioactive decay in terms of applications of exponential functions. Hope you enjoyed. As always, if you enjoyed, please like this video, consider leaving a comment, and if you enjoy the channel content, please subscribe. We publish several new topics every single week. Thank you.